Can all of you see the board and hear me?
Yes, sir, we can see and hear.
Okay, thank you. So essentially in the last class, what we were doing was that we were essentially saying that, here is the enzyme on the surface, essentially, and you have a film of liquid around this. So the liquid is flowing like this. There is a S bulk at the surface, but at the interface where the enzyme is actually sitting, the surface S is some which is the concentration which the enzyme sees, and this then is what the enzyme is seeing. So actually you are measuring this experimentally. This is your experimental data. So therefore, this diffusion rate essentially makes sure that S is less than S bulk, and because of the diffusion coefficient, and as a matter of fact, the driving force Ke into S bulk minus S is actually also equal to the rate of reaction, which is Vm S upon Km plus S. And so for all practical purposes, effectively when you plot V versus S bulk, because this is what you're plotting, you get a plot like this. But the true plot is actually like this, right? And this therefore the because obviously when S bulk is this much and you're getting a reaction rate equal to this, the real reaction rate is this much, isn't it? Because this is S and this is S bulk. And this is what you're measuring, and this is what you're actually having. So obviously, that is why you have a increase in Km apparent, which is obviously greater than the true Km value, the Km true. And this is how you solve the problems. And I talked about damp Polar number, etc., etc. So any questions in this? Of course, the problem becomes complicated, or because in a real reaction, you will be having pellets and you will have liquid running through. In this case, S bulk. And this S bulk will decline over time to come out as S out bulk, right? And so you will have to integrate this function with respect to this expression here, and while your expression here is this one. So your S out and therefore the substrate concentration that will be around this enzyme substrate concentration will be lower than this substrate concentration. So all the time there is a drop, and so your conversion rates will be lower. So I want you people to think about this problem and try to solve it. If you can't, come back to me. But this is an assignment that I'm trying to give you, that you please note this thing and tell me what is going to then happen in a column where reaction takes place without external mass transfer and with external mass transfer. What happens when it is without mass transfer, external mass transfer, and what happens when it is with mass transfer. So I want you to work it out as a problem and tell me what is the degree of conversion. And that brings me to that very interesting question that I was asking you, that we did calculate volumes, the volume of the reactor required by the surface area calculations. You know the volume calculation, which is easy enough. But that will tell you what is the volume of the reactor, which will tell you the volume of the beads, because that's nothing but that the volume into 1 minus epsilon, because epsilon is the word volume. And from this volume, using the specific surface area calculation, you can find out the surface area of the beads. And then if you know the loading, you know the enzyme loading. And from there, you can find out the Vmax, etc., etc. And from there, you can calculate what is the volume of the reactor required. But obviously, the volume required will now be larger because you now have mass transfer. That's point number one. Point number two, which is more interesting, is that when you find out the larger volume of reactor required, you will also have to calculate what is the kind of L by D ratio that you should use. And notice that This is where the problem becomes interesting, because as the L by D ratio increases, as your cross-section area reduces, goes down, and your length goes up, you have actually, your velocity will increase. And as your velocity increases, your Ke goes up as well. Because mass transfer effects, the film that is surrounding this liquid is obviously a function of velocity. And not get into all these things, rather than mentioning this to you, because I'm not going to get into pure chemical engineering here. And as you increase velocities, this film mass transfer coefficient is a function of the velocity of liquid. You know that, right? You're familiar with this statement? And there are correlations available for correlating Ke as a function of velocity. And the graph is like this, of course. It's again asymptotic. So you want it to increase, but beyond a certain point, the increase in velocity does not increase the Ke too much. And so you want to operate somewhere here, not here. So because if you keep on increasing velocities, Ke will not increase significantly, but pressure drops will tend to go up very fast. So you cannot have very narrow and so, interestingly, a column which is a fat, broad column will have lower conversion than a tall, long column with the same volume. Primarily because the volume is the same, everything is the same, but your mass transfer impact is lower because your Ke has become higher, and therefore the Damp-Coulomb number has become smaller. And as Damp-Coulomb number falls, Ke sort of increases, because Damp-Coulomb number is Vmax upon Ke into S0. So Ke is increasing, so Damp-Coulomb number goes down, so your conversion efficiency goes up. So how thin, without compromising pressure drop, you should try to make it as tall and as thin as possible. And that is the kind of experiments that you need to do to see what is the conversion here and what is the conversion here. These are some of the more practical industrial applications of such analysis vis-a-vis mass transfer. Is this argument clear? Let us we will come back to this if we have time, because we have many things to cover, but at least you should be aware that mathematical correlations exist for this, and which can be used to calculate Ke and therefore predict Damp-Coulomb number, and therefore predict what is the kind of conversion that you will get after post-integration. Okay, now, unfortunately, the real situation is that not only is enzymes, because the surface areas are very small, and so you obviously want the enzyme to be entrapped inside the beads. You just don't want it on the surface, you also want them inside the beads, because these beads are usually made up of, all beads that, as Kshitij would have shown you in the lecture, are crisscrossed with fine porous structures, and these porous structures actually then provide a much larger surface area. So each of these pores allow you to entrap and to stick enzymes, and these fine porous structures then allow the enzyme loading in a bead to be much higher, because this surface area available in the pores is actually much larger than the surface area available only on the surface. And so enzyme loading can be significantly higher in porous beads rather than solid beads. And we almost always use porous beads for our calculations. And porous beads means now you have to consider the fact that there is diffusion taking place, and from here to here, from the surface area here to here, to R is equal to 0, so if R is equal to 0 here, and R is equal to R here, R is equal to R here, the substrate concentration will tend to fall. The substrate concentration here, let us assume that this is the substrate concentration in the bulk. Let us forget external mass transfer, we are not combining it. Let us study one at a time. So internal mass transfer would obviously mean that your substrate concentration bulk is here, but inside the bead your substrate concentration tends to fall. And so your reaction rates will also tend to fall, because your substrate concentration here is actually falling. So your effective reaction rate is this section will have some other reaction rate, this section will have some other reaction rate, this section will have, these are various, as you can see, you can do flat plate geometry. I do not know whether you have done this or not, but I'm sure somebody would have done this in differential equation course. Then you have to sort of see that this is the annulus, and you can set up your mass transfer equations for r is equal to r to r is equal to 0. These are the two boundary conditions, r is equal to 0, and this is the zone, for example, is this zone here, and your concentration is falling, and so your net reaction rate of the immobilized enzyme is internal mass transfer plus enzymatic reaction or reaction, and that is obviously lower unless the substrate concentration fall is all zero order. We'll come to that later. That's a rather oversimplified situation. So what do? You set up your basic mass transfer. So equations, you are familiar with this kind of setting up the model. R is equal to 0. This is the flux of substrate coming in. Let us call it W or F, whatever you want to call it. And so you set up the material balance on this annulus, which is, delta R. And what do you have? You have this W, whatever, W is now, the flux is also a function of R. The W is the flux, the W which is a function of R, or I will call it sort of simply WR. I mean, why am I writing it like this? Okay, so WR is the flux per unit surface area, right? Which is, into 4 pi R square, which is the surface area of this, with R is the radius. Of course, I should have written it as R. Okay, let me write it. R at R plus delta R minus W. Okay, W. This is R plus delta R, right? WR 4 pi R square at R is equal to R. At R is equal to R, right? Is equal to the rate of reaction, which is per unit volume. So Rx into 4 pi R square delta R. You're all familiar with this kind of formulation. The volume is 4 pi R square because this is a very thin annulus into delta R. Or if you want me to say, I can put mean here. R square mean into delta R. All of you are familiar with this kind of formulation? Hello? Yes? This kind of material balance, all of you are familiar? Can I go ahead, or is it something not so obvious?
Sir, we can go ahead.
Yeah, so you are familiar with this, right? So WR, by the way, is also the flux. I mean, I should have called it FF, which is your diffusivity dE dC by dR, right? And reaction rate, let us say Rx is let us say Kc raised to n as an nth order reaction rate. I'm not writing the other equation, which is the actual enzyme kinetic equation. I will explain in a minute why. So this is it. Right, dC by dr. So what is the formulation now? Please tell me. D, and this is, we substitute dC by dr here. Okay, W instead of W we write dE dC by dr. Go ahead. Right, into, and now what does this simplify into? The top one. I hope you can see that 4 pi R square, 4 pi R square, 4 pi R square is all gone. Right, and so this equation here, so was, and then divide by delta R here. I hope you can see this. So you divide by delta R, we have dW R upon dr, right, is equal to Rx. Okay, sorry, Rx into R square. क्या कर रहा हूँ मैं? Hello.
Sir, Rx.
क्या होगा? Rx होगा और सिंपली Rx होगा. क्या होगा?
Yes, sir, Rx.
This expression is what? Okay, let me sort of let me sort of create some space here. I thought you are familiar with this stuff, so I thought I would just sort of ask you. अरे भाई क्या हो रहा है? Okay. So what is this equation? D of dr, this W 4 pi we will cut out, WR R square by dr is equal to R square into R reaction, Rx. Okay, is it all right?
Yes.
ठीक है?
Yes, sir.
Yeah, and this WR is this. This is this, right? WR is this. This WR is this here. So we write, and reaction rate is K series of N. So we write D of dE dC by dr, right, into R square upon dr is equal to R square into Rx, Rx or R reaction. Rx, मैं Rx लिखता हूँ सिंपली, है ना, Rx लिखता हूँ, ठीक है, ये क्लियर है? And as I said, this is equal to Kc raised to n. So now tell me what is this expression on top here? This is, let us take dE out, which is a constant. So derivative बताइए क्या होगा? R square first function, second function, भाई बहुत मुश्किल नहीं है. R square d2c by dr, right?
Yes, sir.
Hello.
Yes, sir.
Plus 2r. आप बोलते रहिए, हाँ, अब ये सर मत बोलिए.
DC upon dr.
dr is equal to R square into reaction rate, Rxn, right, into reaction, which translates to, come on, R square से डिवाइड कर दीजिए, D से भी डिवाइड कर दीजिए, इसको फर्स्ट फंक्शन ले लीजिए, स्टैंडर्ड डिफरेंशियल इक्वेशन फॉर्म में ले आइए, जो आप लोगों को चाहिए. दिस इज समथिंग व्हिच यू आर फैमिलियर विद, dc by dr square plus
2 upon R dE
plus dc by dr, है ना, is equal to Rx upon dE. ठीक है? This is the familiar form of equation you are all familiar with. ये spherical coordinates में यही आता है, यही आता है ना आप लोगों का, ये तो आप लोगों को familiarity है, which is equal to, of course, मतलब if you want to say K series of n by dE, ठीक है, into R square, of course, this part is equal to this. Okay?
Yes, sir.
हाँ, मतलब तो ये वाला पार्ट, ये वाला फंक्शन ये हो गया, ठीक है ना, because this is K series of n upon d. Okay, now can you sort of solve this? You know the standard methods of solving this. आप लोग ने ये किया होगा. So first of all we have to sort of make it dimensionless. So what are the dimensionless variables that we choose? We choose say psi, आप लोगों को मर्जी है, मतलब psi y लगने से अच्छा लगता है देखने में, which is the dimensionless Ca upon Cas, right? Where Ca is this, as I said, the substrate concentration at the surface, and Ca is a function of, this is Ca somewhere here. Ca is a function of R, right? So the dimensionless quantity where psi goes from 1 at R is equal to R to some value less than 1 when R is equal to 0, whatever. Okay, and then R upon R is also taken as lambda, which is R upon R. And so we simply say Ca is equal to CAS, which means CA is equal to CS at R is equal to R, at R is equal to R, which really simply means that phi is equal to 1 at lambda is equal to 1. Okay? Yeah? Yes? Okay. And I will make another assumption which is not really correct, but I can do it two ways. See, there are two boundary conditions. One is this boundary condition, which is CA is equal to CS, or rather at R is equal to R, which really is this boundary condition BC. But you need two boundary conditions, the second order differential equation. Now at lambda is equal to 0, at lambda is equal to 0, what is the boundary condition? Which is what is the correct boundary condition? Anybody? भैया आप लोगों ने किया हुआ है. This correct boundary condition is obviously by principles of symmetry. हेलो, हाँ बताइए. आपका मैंने प्रोफाइल बनाया था ना, आपको याद होगा, ये प्रोफाइल ऐसे करके बनाया था. इस प्रोफाइल में एक खास बात होगी, इधर से भी प्रोफाइल होगा ना, आर स्क्वायर सर्कुलर है ना, ये स्फीयर है. दिस इज स्फीयर. So the boundary condition at the center point of the sphere is determined by what? By symmetry conditions. You can see by symmetry conditions that there is no flux going to the other side, right? Do you realize this point? Hello? All of you are with me? So यहाँ पे कोई flux नहीं होगा. At the point 0 there can be no flux from this side. So I cannot have a flux coming in here and also going through this side, because there is flux also coming in from here, and flux coming in from here, and flux coming in from here. So really what is the boundary condition?
Flux is equal to 0.
अरे भाई, सिमेट्री कंडीशंस में डेरिवेटिव 0 होता है, फ्लक्स 0 होगा, ठीक है ना. तो इसके टर्म्स में यू आर एब्सोल्युटली राइट, फ्लक्स इज इक्वल टू 0, व्हिच रियली मींस दिस बाय दिस is equal to 0. ठीक है ना? Hello?
Yes, sir.
By symmetry principles, this is the secondary boundary condition. D psi by d lambda is equal to 0. But what I will do is, I can use this and prove it. I will take a simpler boundary condition, which is a very simple requirement. I will say psi is finite. It is non-zero. मतलब the enzyme is not exhausted. यहाँ पे भी reaction हो रहा है. It is not 0, which is not always true, but I can take this as a easier boundary condition. This is the more correct boundary condition that I should take. But so the two boundary conditions at one is this: at lambda is psi equal to 1, lambda is at lambda equal to 1, psi is equal to 1, and at lambda is equal to 0, psi is finite. Psi is finite. So these are the two boundary conditions that I will use, and then I will convert this equation first in terms of lambda and psi, lambda and psi. So given this basic equations, that where did I write it? Yeah, here. Where did I write it? Here. So psi is equal to CA by CS, lambda is equal to R by R. Okay. So these are the two boundary conditions. So and obviously we wrote W or the flux is equal to d dc by dr. So that is how we derive it. Anyway, that's all right. So now what is dc by dr? By dc by dr क्या है? dc by dr है यहाँ पे ना. तो dc by dr क्या है भाई? स्टैंडर्ड वो बताइए ना, चेन रूल. dc by d lambda, right, into d lambda by dr. अरे भाई आप लोग बोलेंगे नहीं तो बड़ा मुश्किल हो जाएगा. इज इक्वल टू dc by d phi into d phi. This is what we want, right? d lambda into d lambda by dr. ठीक कर रहा हूं मैं? dc by d lambda by dr, d lambda, yeah, ठीक है. ओके.
Yes, sir.
हाँ, तो क्या हो गया ये? अच्छा, dca by इतना, ये मैं बाउंड्री कंडीशन वाला मिटा रहा हूँ, so that I want to keep this here. मैं इसको मिटा देता हूँ, ये तो हो चुका है, ये वाले सॉल्व कर चुके हैं, है ना. बताइए. Related and write it in black, so that's so very obvious, है ना? So what is dc by d lambda? You know, dca by a लिखूं या by d phi क्या है?
Sir, it will be 0 at
CAS भाई. अरे ये देखिए ना, ये वाला dca by d phi, ये तो मैं सिर्फ डायमेंशनलेस क्वांटिटीज के टर्म्स में कन्वर्ट कर रहा हूं. CA by CAS is equal to phi. So dca by d phi is nothing but CAS, right? Hello?
sir, how it will be?
है ना? हाँ? Hello?
Sir, I'm not understanding how it will be.
अरे भाई ये वाला ये मैंने चेन रूल लगाया.
Yes, sir.
Sorry, I should not talk in Hindi. I get agitated when talking in Hindi. So dc by dr निकालना है क्योंकि आपको इस इक्वेशन में सब्स्टिट्यूट करना है. This is the basic differential equation. Okay? Can you see this? d2c by dr square is equal to plus 2 by r dc by dr is equal to rx upon de, which is kc raised to n by d. Okay?
Yes.
Okay? This is rx is kc raised to n. ठीक है ना? अब I want to now convert. I don't want to use dc and I don't want to use r. I don't want to use c and r. I want to use dimensionless quantities given by psi and lambda, where psi is equal to ca by cas, goes from 0 to 1, and lambda r by r, which goes from 0 to 1. ठीक है?
Yes, sir.
इतना क्लियर हो गया? अच्छा, now dc by dr निकालते हैं. पहले इस एक्सप्रेशन को निकालते हैं. dc by dr, dc by dr का हो जाएगा dc by d lambda into d lambda by dr. ठीक है?
Yes, sir.
एंड dc by d lambda, अब c को हटाना है. dc by d lambda की जगह आपको लिखना है d lambda by d psi by d lambda. So dc by dr की जगह आप लिखिए dc by d lambda into d lambda by d psi by d lambda. ठीक है?
Yes.
ये वाला एक्सप्रेशन, ये वाला मैंने इसको इन दोनों पार्ट्स में कन्वर्ट कर दिया और d lambda by dr लिख दिया. So dc by dr is equal to dc by d lambda into d lambda by d psi into d lambda by dr. This is the term that we are interested in. Right? Because this is the term I want to put here instead of dc by dr. Right? So we have to find out dc by d lambda and d lambda by dr. And these are constants because dc and lambda are connected as ca is equal to cas into phi. So dc by d lambda is nothing but cas.
Yes, sir.
ये वाला एक्सप्रेशन देखिए, है ना? ये तो बस प्रोपोर्शनैलिटी है ना. ये तो डायमेंशनलाइज किया है ना हमने सिर्फ प्रोपोर्शन से मल्टीप्लाई कर दिया. ये मतलब 1 ग्राम से 100 ग्राम हो सकता, मतलब 0 ग्राम से 100 ग्राम हो सकता था. अब 100 ग्राम मैक्सिमम CAS है, तो मैंने इसको 0 to 1 करने के लिए आई हैव जस्ट डायमेंशनलाइज्ड इट. आई हैव ब्रंग इट 0 to 1 ना. आई हैव जस्ट सॉर्ट ऑफ मेड इट प्रोपोर्शनल. ठीक है ना? तो इसका डेरिवेटिव सिंपली उतना CAS टाइम्स होगा. तो dc by d phi is nothing but CAS. dca by d phi is equal to nothing but CAS. And similarly क्या है? d lambda by dr. d lambda by dr क्या है? हेलो, d lambda by dr ये दिख रहा है आपके सामने भाई? हाँ, 1 by r. ये तो बोलिए. हाँ, तो आप लोग थोड़ा सा अपना माइक्स ऑन रखिए. ठीक है ना? तो ये हो गया dca by d lambda is equal to dCAS, d lambda by dr is equal to 1 upon r. ठीक है? Okay?
Yes, sir.
Okay. So therefore what is dca by, हमको basically dca by dr क्या हो गया? फिर dc by dr क्या हो गया? Is equal to, from this expression here, dc by dr is equal to CAS upon r into d phi by d lambda.
d psi by d lambda.
D lambda. This is what we have, right? So this is what we get as an expression. dc by dr is equal to CAS by RA d phi by d lambda. So which we can substitute in this expression here, in the bottom here. Okay?
Yes.
Okay. And now tell me what is, and I will, मैं इसको रब आउट करूं?
Yes, sir. We can.
So sorry. Pura उड़ गया. I'm sorry. So let me write it out again. Yeah. So we have now the original expression as, what was the original expression? Now I've forgotten. Please tell me somebody. D to C
upon dr square
by dr square plus 2 by r
upon dc by dr
is equal to
rx upon de.
Is equal to rs upon
De.
rx, or rather kcas
Power n
kca
upon d.
kcs था नहीं, kca था ना,
kc
rest
upon
of
n. Yeah.
हाँ,
upon
kca rest of n
upon de.
upon d, ये था ना. And now we have dc by dr
Sir, there's a
is
DC
equal
by
to
DR missing in the second term.
dc by dr is equal to हाँ ये हाँ sorry, यहाँ मैं मिस कर दिया, sorry, I'm so sorry. dc by dr is equal to this, ठीक है ना?
Yes, sir.
Okay.
Yes, sir.
And now dc by dr we just now discovered is equal to d phi by d lambda
ca upon r.
ca upon, ये मुझे भी cas upon r. Okay. And I will not do this, but I hope you understand this. d2c by dr is equal to d2 phi by d lambda cas upon r square. ठीक है ना?
Yes, sir.
अब obvious है ना, cs upon r square. और इसको मैं वापस सब्स्टिट्यूट करता हूं. So then I write this expression here as d2 phi. Sorry, इसको मैं लिखता हूं d2. I will not spend too much time now. I will go fast because ये प्रॉब्लम होता है ऑनलाइन टीचिंग में. Upon cas by r square, ठीक है ना, प्लस 2 by r है lambda r, ठीक है, d phi by d lambda into cas
Yes.
by r is equal to rx by de. ठीक है? Okay? All of you okay with this? Huh? So let us multiply all these equations by cas by r square. So we get back to this form. We get this back version d phi. मल्टीप्लाई बाय सी एस बाई आर स्क्वायर क्या होगा, प्लस 2 बाई ये आर स्क्वायर हो गया ना, 2 बाई लैम्डा is equal to, now let me call this as k cas rest of n, c rest of n, ठीक है ना?
Yes, sir.
kCa rest of n. Now what is kCa rest of n? Suppose it's nth order reaction. What is kCa rest of n is equal to k, come on, we just now said
to the power n.
huh?
Psi
Ca by
Ca
Ca
power n.
cas, right? So it is k Ca rest of n into psi rest of n cas rest of n. ठीक है?
Yes.
Okay, so this is this. Okay, so now multiply by cas square. So what do we get? Is equal to k psi rest of n cas rest of n into dividing by cs. So n minus 1, ठीक है? हेलो, n माइनस 1 हो गया ना, और ऊपर आर स्क्वायर आ गया अपॉन डी. Is this okay? Into is equal to 0. So is equal to this. So bring it this side, minus this is equal to 0.
Yes, sir.
Okay? Are you fine with this?
Yes, sir.
So I have now got, so this expression here. No, not this one. इसको हटा लो, इसको हटा दो, इसको हटा दो. So we can write this as this here, same thing here. I will not repeat. Okay, let me write it. How does it matter? Plus 2 by lambda minus, and let me take this as phi square lambda square. Lambda is sort of n actually, right? Is equal to 0. Okay? Are you getting this?
Yes, sir.
Huh? So now let us look at this expression here. What is phi square here? What is this phi? What is this phi? Can you see what is this phi? I put phi square deliberately. I hope you realize why, but even if it doesn't really matter. What is phi square? K CAS
to the power
n minus 1 r square upon d. Do you realize this expression? Now look, forget the algebra for the time being. Look at this expression here. What is this? It is actually K, मैं मतलब approximately कर रहा हूँ, CAS रेशो ऑफ n, थोड़ी देर के लिए मैं n से करता हूँ, ठीक है ना, into, let me say I multiplied by 4 by 3. Now I don't know what whether I'm making it making sense or not. I'm trying to sort of, and pi r cube divided by DE, and I have to divide by CAS again because I've got, and I will write CAS minus 0. I hope you see what I'm doing here. And r cube किया है upon r, है ना, ये r square है ना, into 4 pi r square. Forget the constants. See what I'm doing? This is r cube हो गया ना, ये r cube upon, ये r cube है, ये r square है, r है, r square से मल्टीप्लाई किया, r से डिवाइड किया, तो r से डिवाइड किया, ये r square हो गया. Notice that r का डायमेंशन सेम है.
Yeah, yes, sir.
You get the point? R cube, r square, r. So you see what I'm doing here? And n से divide किया, CAS से multiply किया, CAS से divide किया. So notice what is this? This is some measure of the maximum reaction rate. Total volume reacting at K CAS of n. And this CAS minus 0 into 4 pi r square.
Total diffusion.
This is CA minus 0 upon r. This is the you know, the gradient, and so in some ways a measure of diffusion.
Yes.
And this is in some ways a measure of reaction. So phi square and the damp polar number that we were deriving were very, very similar things. You get my point? Remember the same damp polar number we had derived for the external mass transfer. So this expression here, I mean, of course, I've written it in such ways, but this expression has the same dimensions. This expression here has the same dimensions of the kind of dimensions that we were talking about in the damp polar number. Okay?
Yes, sir.
So phi square is in a sense a physical measure of the damp polar number kind of expression, and we have now a very simple expression, this kind of differential expression, which is now in terms of dimensionless quantities. And of course, notice that for enzyme kinetics, I mean, it is exactly similar to this expression here. Okay, but we have got it now in terms of dimensionless quantities. This one was in, so this to this is just a transition. So I will rub this part out, and we now need to solve this expression here with all the boundary conditions that we had talked about. All of you with me till now? We need to wrap this up very quickly now because we are taking a lot of time solving a simple differential equation, but I want to go slowly. Okay, so this is your basic differential equation, and of course you remember your enzyme kinetics. It is either 0th order or first order. And so if it is 0th order, as I pointed out, it does not really matter, because if the substrate concentration here is S bulk or CAS, as I said, S bulk or CAS, whatever term we use it, or CAS, if this is too high and it falls from here to here, as far as I'm concerned, velocity does not change. 0th order reactions, too much of substrate, there is no question of mass transfer. Mass transfer is taking place, but the reaction rate is not going to change. Velocity is not going to change. The really velocity changes at this point. Where substrate concentration is this, falls to this, the velocity falls. So really, this part is the first order part. So we are really concerned about the first order reaction kinetics. And so we can take n is equal to 1. And if we take n is equal to 1, then phi square becomes equal to, come on, it becomes equal to, this disappears, k r square upon d, right? Or rather simply phi is equal to r root k by d. So phi is equal to this term. Okay?
Yes,
For
sir.
first order reaction. Right? And this is your differential equation here. Now, do you know how to solve these differential equations? Are you sort of familiar? No. आप लोगों ने किया होगा बहुत पहले कभी, ये सारे circular coordinates में ये basically I hope you know that. I mean really the problem is that this term here is what is causing the irritation. ये वाला होता तो easily solve हो जाता. Now ये गायब हो गया ना, n 0 हो गया तो ये गया minus phi square. ठीक है ना? So what do? So मैंने कुछ गड़बड़ कर दिया. Phi square lambda phi psi होना चाहिए था. N is equal to 1, not n is equal to 1. Sorry. This is not disappeared. What am I doing? This is phi square psi, but that is all. N is equal to 1. So this kind of expression, I'm sure you are familiar that this is the part which has to go away. And for that you do this, I do not know whether you remember this. Y is equal to lambda into psi. This is the kind of, you do this. Or lambda is equal to whichever way you want to write it. Psi is equal to y upon lambda. ये आप लोगों ने substitution कभी किया है? Because you know what happens when this case is that d psi upon d lambda क्या होगा? ये d psi upon d lambda चाहिए ना? तो y के terms में क्या होगा? d psi upon d lambda, ये आप लोगों ने नहीं किया होगा? Take this expression here. So u by v form है is equal to lambda dy by d lambda, right? Minus of course just y upon lambda square. ठीक है? Hello? Which is actually equal to what? 1 upon y dy by d lambda. Am I writing it right? Minus y upon lambda square. So you know this kind of, ये जो expression है, ये आप देख रहे हैं आप, ये पूरा expression d psi by dy के टर्म में सॉल्व हो गया. उल्टा कर दिया क्या? नहीं, ठीक है. And what about d2 psi by, so this d psi by d lambda here, I hope you're getting this. This here, is this here. Why don't you do it? I mean, and let me write it out. Let me write the second expression, that's obvious, which is d2 psi by d lambda square, this one here, okay, d lambda square is equal to what? In terms of y? आप लोग बोल नहीं रहे हैं कुछ भी. y के टर्म्स में क्या बनेगा बताइए. I mean, really, what I'm trying to ask you is a very simple thing. I am asking you the whole exercise. I mean, if you don't understand, follow, then please tell me what I'm asking, and I'm waiting for you people to answer. I really want to get rid of this. I want to write this expression as d2y upon d lambda. ये क्या होगा? So I've written, my substitution is the following. Psi is equal to y by lambda. Psi is equal to y by lambda. So now, please tell me, how would I write d psi by d lambda in terms of y, in terms of more importantly, how would I write d2 psi by d lambda square? करिए आप लोग थोड़ा सा. I think you've forgotten your maths, or you remember your maths? Okay, let me tell you the answer. d2y by d lambda square plus y square y is equal to 0. ये lambda यहाँ पे गायब हो जाएगा, यहाँ पे y आ जाएगा. So I will get an expression like this. This term I am able to get rid of it. Now this differential equation is easy to solve. Do you get this or not? Let me wait for 5 minutes. Using this substitution, psi is equal to y by lambda, I am able to reduce this equation d2 psi by d lambda square minus 2 by lambda d phi by lambda. I am able to get rid of this expression and write it in terms of simply d2y by d lambda square and psi square y is equal to 0. I am able to get rid of this by this substitution. Can you get rid of this? By using this very simple expression here. अगर हो रहा है तो बताइए, नहीं हो रहा तो बताइए. Please try it out. I'll give you 2 minutes. I can't see your faces, so I do not know whether you're trying it out or not. That is what confuses me, and I tend to get impatient. But I will not get impatient. I want you to derive it. Are you able to derive from this red expression, this expression here? Otherwise, we'll do it. Okay. Let us say that you will be able to do this. Go back and do this. I suppose you are getting the feel of this. This is a fairly standard methods of solving differential equations. So I thought you would be familiar. You might have just forgotten. You will recover this. I'm telling you the substitution to be used. Psi is equal to y by lambda. I'm telling you the basic derivatives to be used, and then substituted in d psi by d lambda, d2 psi by d lambda, and d psi by d lambda, and phi square lambda. And then you will see that this expression then reduces to d2y by d lambda plus phi square y is equal to 0. And can you tell me what is the solution of this differential equation? This is obvious. ये substitution आप करेंगे. अब आप मुझे इसका solution बताइए. What is the solution to this equation? अच्छा मैं इसको भी मिटा रहा हूँ. Okay, psi is equal to y by lambda. Please remember this. So this solution, I hope you all know, is y is equal to, I hope you know this, right? A1 cos hyperbolic phi y phi 1 of phi, of course, phi lambda by not y, phi lambda plus b1 whatever, some constant, sine hyperbolic. If it was minus, it would be cos plus sine. If it is plus, it is cos hyperbolic and sine hyperbolic, right? Phi lambda. Right? Okay. And y is what? अब psi पे आ जाते हैं इसको. Psi is equal to therefore a by lambda cos hyperbolic phi lambda plus b by lambda sin hyperbolic phi lambda. Okay, all of you with me till now? Okay, and notice now I will use this basic concept. Since at lambda equal to 0, I said phi is non-zero. It is finite. That is the other boundary condition. At lambda is equal to 0 boundary condition. So at lambda is equal to 0, at lambda equal to 0, notice this at lambda equal to 0 sine lambda, that becomes 0, so that this tends to 1. Sine phi lambda upon lambda, that is an easy solution. But here this tends to 1, this will tend to infinity. So by definition, from this boundary condition, I can actually say that a is equal, from this boundary condition, I can say a is equal to 0. If phi is finite, so I can use a much simpler boundary condition and say that this expression, this term here is 0. So phi becomes equal to b by lambda sine phi lambda, sine h, sorry. And now we can use the other boundary condition, which is lambda is equal to 1. What is phi? Is phi equal to? Phi क्या है? CA by CAS. क्या होगा lambda equal to 1 में? अभी बताया था. 1. Okay. So if this is true, then what is the value of B? भाई ये तो आप लोगों को बताना पड़ेगा. बाउंड्री कंडीशन सब्स्टिट्यूट करके तो बताइए. Come on. So what is phi equal to? Psi is equal to? We have psi is equal to b by lambda sine phi lambda. We are running out of time. So 1 is equal to b by lambda, और 1 ये भी तो 1 है ना. So b sine phi. Okay. So b is equal to 1 by sine phi. Okay. And so we have lambda is equal to, or CA by CAS is equal to, come on, sine upon lambda sine. ठीक है? So we have this as the profile of CA by CAS for a situation with mass transfer coefficient, where psi is equal to, oh, I hope you remember what psi was, right? And so really let us end it here by simply saying that, end the class here by simply saying that this plot can be made. So you know, I can sort of say that this is my R. This is, now let me put R here as R maximum and R here as 0, and CA versus CAs, and this is the kind of plots that we're going to get. Now can you tell me which is larger phi and which is smaller phi? So this is, I hope you realize, small phi, and this is large phi. Right? So psi is small, I mean obviously fast diffusion, and so the profile does not drop too much, and slow diffusion profile drops. So, and this is the basic, I mean I've run out of time as well as ink, so let me stop here, and now we will find out what is the enthalpy, what is the efficiency, etc., etc. Can you hear me? Hello?
Yes, sir, we can hear.
Hello?
Yes, sir, we can.
Yeah, so now I leave it to you to find out what is efficiency. Actual rate upon rate without diffusion. rate. Next class we will do this tomorrow, but I wanted to find out. आपको CA by CA पता है, इसको इंटीग्रेट मत करिएगा प्लीज. I hope you realize इसको इंटीग्रेट करके सॉल्व करना one method है, but what is the trick that you will use? The trick you will use is that एक ये बॉल, इस बॉल के ऊपर आप इंटीग्रेट कर सकते हैं given the profile, but far simpler trick would be to look at the slope at this point, C by CS, and this slope with the diffusion rate is actually equal to the rate of reaction by steady state logic. Am I making sense?
Yes, sir.
So instead of integrating and finding out for each point what is the velocity and multiplying by reaction rate, which now we are saying is V is equal to KCA only, first order reaction ke liye kariye aap only. Now we will simply use the fact that we find out the rate of diffusion at this point from the slope of this line, and from the slope of this line we find out the rate of diffusion by multiplying by dA, and we have solved the problem because of steady state. I don't know whether I'm making sense or not. We'll derive it in the next class. Think about it. Okay, so is this clear? What is the profile of the CA, which is this is the profile of the CA. Sine hyperbolic phi lambda upon lambda sine hyperbolic phi. So stop here. Next class we'll discuss. Tomorrow we'll discuss this. Is it clear? I hope these are differential equations which you have solved earlier, but just forgotten. I'm sort of reminding you. Cos hyperbolic, sin hyperbolic तो आप लोगों ने किया होगा, है ना?
Yes, sir. We have done that.
हाँ तो भाई ठीक है, इसमें फिर हमने सिर्फ सब्स्टिट्यूशन ही तो किया है और कुछ नहीं किया. बस y is equal to वो sorry is equal to वो lambda into 5 वो वाला बस सब्स्टिट्यूशन ही किया था बस y का. चलिए. Any questions? Shall I stop here?
Yes, sir. We can stop.
Thank you.
Thank you, sir.
Okay.